Okay, for this video, we'll be going through how to derive the center of mass equation that we are familiar with in NCEA. Okay, so we have this setup where we have two masses. M1 is clearly more massive than M2, and these two masses are held together by some rigid pole thingamajiggy. For simplicity purposes, this pole does not add to the weight of the entire system, or the mass of the entire system, so you could say it's negligible. But that pole is holding those two masses rigid in place. So, in this case, there is going to be a point. Let's say it's right here somewhere. At this point, we can place down a pivot, just like a little seesaw, right? And at this point, the masses will be balanced, and so they won't tip either backwards or forwards. You can imagine if I instead put the point right here, you can imagine that M1, since M1 is way more massive than M2, the whole system is just going to tip lopsided, right? So M1 is just going to fall that way. It's going to have an angular acceleration in the clockwise direction. Let's say we put the pivot back to where it was. We can imagine at this point the two masses will not rotate downwards and will just stay flat. And at this point, this is the center of mass. And so the goal for this video is to try and find this point right here. How do we derive a formula to get that point? So in order to derive this formula, we can set an arbitrary reference point, which will be this line right here. And we have some distances that we have derived from that reference point. The first distance will be x2, and that is the distance between the reference point and the mass m2. The second distance will be the distance from the reference point to the center of mass, which we call x center of mass. And the third distance will be from the reference point to m1, which is x1. Now, as discussed previously, in order for the system to be balanced, and therefore meaning being balanced, there is no angular acceleration. Therefore, the sum of all torques must equal 0, right? Because as we know that alpha is equal to the torque over the rotational inertia. So if there is a torque present, therefore there must be an angular acceleration. So in order for there to be no angular acceleration, torque must equal 0, which we have discussed up there, where the sum of all torques must equal to 0. So in order to get the sum of all torques, we need to derive some general formulas for the torques produced by M2 and the torques produced by M1. So the torque produced by M1, as we know that T is equal to Fd, where our force is just our weight force, which is mg. So our torques of M1 is going to equal to M1 g, and our distance value, our d, is going to be the distance from the pivot. So it's this distance right here. And to derive that distance using our reference point and our given distances, we can say that this distance is equal to x1 minus the x center of mass. If we take x1 and we minus the x center of mass, we get this value here, which is the one that we want. So we can say x1 minus x center of mass. Okay, now moving on to the torques produced by M2, we can say similar thing, M2g x2 minus x center of mass. Now you might be thinking, why did we do x2 minus x center of mass when logically we should have done x center of mass minus x2, right? Because that would have given us this distance right here, which is the similar thing that we did on the previous one. However, we did x2 minus x center of mass, as this gives us a negative value. The reason why we want a negative value is because M2 is producing an anti-clockwise torque, whereas M1 is producing a clockwise torque. The reason why this is important is because the sum of all torques must equal to 0, so therefore T1 plus T2 has to equal to 0. So you can imagine if one of these values isn't negative, it's impossible for this to equal 0, unless both T1 and T2 equals 0, which we know in this case is not true. So using x2 minus x center mass to give us a negative distance will give us a negative torque, which just means torque in the anti-clockwise direction. Okay, so we know that the sum of all torques has to equal to 0, so therefore T1 plus T2 has to equal to 0. Thus, M1 g x1 minus x center of mass plus M2 g x2 minus x center of mass has to equal to 0. Now we can divide both sides by g in order to cancel out these g's, and we get m1 x1 minus x center of mass plus m2 x2 minus x center of mass. And that is all equal to 0. Now expanding this out, we get m1 x1 minus m1 x center of mass plus m2 x2 minus m2 x center of mass. And again, that all equals to 0. We can collect some like terms here, as there we have two values with x center of mass. We can gather that and factorize x center of mass out. So we get m1 x1 plus m2 x2 minus x center of mass, and then we can factorize x center of mass out like that. And that will equal to 0. So you can see how we factorize x center of mass out of these two values right there. Now we can move this onto this side, and we get m1 x1 plus m2 x2 is equal to the x center of mass m1 plus m2. Now we can divide both sides by m1, m2, and we get m1 x1 plus m2 x2, and that is all over m1 plus m2, and that's equal to the center of mass. And as you can see, that is the formula that we're familiar with. Okay, so this formula works with any number of objects or masses. So if you want to practice, here is a situation where you have we have our reference points, we have our distances, and we obviously have our masses. I have set the center of mass to this point right here. And so if you want some practice, see if you can derive this formula here, which is just the center of mass formula, except now for accounted for 3 masses. As you can see, we've added this section here. So have a go if you want, and yeah, hopefully this helped.